Hello everyone, it's October 2nd. Alright, let's do this. Actually, I need to do this one first. Schedule maintenance. I don't think affects us. Alright, I'm gonna trap rainwater. Oh! Alright, we solved it last time. January. Alright, I remember this. It's a 3D. I don't remember how to solve it, so I'm just gonna read it. Copy and paste. Yeah, once the problem is too hard, it's actually become easy to do because I don't have any intention to resolve it because I forgot how to solve it. But we will read through the whole thing for sure because it's definitely necessary. Alright, let's see. How do we do this? So basically it's, yeah, these heights, and then we want to trap. Yeah, I want to trap the water. To use BFS as an extension of the original 2D solution. The 2D solution was 2 pointers to find the minimum of the 2 borders and progress from the smaller border. So basically it's, if I remember, the 2D solution is you have on both sides, right? And then you find a smaller side. And because it's a smaller side, I actually forgot how the 2D works. Okay, let me think about it. To tracking rainwater. Yeah, you have, I think it's, you know, going from the left, you find the smallest, and then going from the right, you find the smallest. And then you compare wait, hold on, I don't remember. How do we trap rainwater using 2 pointers? I don't remember. Trapping rainwater is where's trapping rainwater? Here. Keep track of the left max and right max. When left max is smaller or equal to right max, and if height low is smaller than left max, then it is guaranteed that the amount of space above height low, but below left max can be collected as rain. We have a left max and a right max, right? So we keep track of the left max to the right max. What we want to know is for each height, is it possible for it to trap rain? Now, if I have the left, like if I'm not the left max, we go left to right, right? So we go left to right, and we have a current, like one side is bigger than the other side, and then we will move the smaller side. So if it's smaller, then because we have higher on the right hand side, right? So it's guaranteed that this amount will be trapped. So we add this, and then we add this, we add this. But if I get higher, the left get higher, then the right can move. So that's basically how we're gonna go. Yeah, we have a low and high, left and right. If left max is smaller equal to right max, will move on the left, right? So if this is smaller than, then we'll add, this is the extra. Otherwise, we will update the left max. Otherwise, we'll go on the right hand side. Okay. All right, so I think this is making things clearer. BFS as an extension of the original 2D solution. In the 2D solution, we use 2 pointers to find the min of the 2 borders, yes, and the progress from the smaller border. In the 3D version, we use the same approach. We find the smallest of all the borders. All the borders, so around. So we find the smallest among all the borders, the outer edge of the grid. From there, we progress using BFS. A min heap can be used to quickly pop the current lowest border, right? If we encounter, so from this border, we'll go. If we encounter a higher cell, we add it to the heap. Yeah, because all we want to do is to get the smallest. Yes, all we want to do is go from outside in and find the smallest, right? Then, wait, hold on. If we encounter a higher cell, we add it to the heap. If we encounter a lower cell, since we know the current lowest border, the amount of water that can be held above it is the lower cell. Like above the lower cell. Difference between it and the lowest border. After that, we can set the water-filled cell to the same height as the lowest and throw it to the heap as well. So we are constantly adding new ones in. Right, it's the same thing with 2D, because as we go, well, the 2D is just as long as it's bigger, then we put it in. But in 3D, we get a lower, because the water cannot be, like if we get a even lower, like that's the ceiling, right? Like why do you push it in? I don't think you should push it in, right? You don't need to push it in. You just don't pop the previous one. But you're doing BFS, so you will have to. Yeah, when the lowest one comes in and then your lowest one get popped. Okay, so we have priority queue, which is a min heap. Heap size, a height size, and direction for the edges, so it's gonna be the outer edge. So what we're gonna push is the height. I don't understand this part. This is the height of each cell. So we have the height of each cell. Okay, height of each cell. So we go J is 0, J is smaller than N. So we are going all the columns, and then 0, J is the first row. Okay, first row. Oh, okay, this is the first row. This is the last row. So this is the height, 0J. Okay, last row. And this is, but I is equal to 1. Because I already put it in, so I equal to 1 is the first column, and then the last column. So we get the smallest out. So we know the smallest. So that's where we're gonna start, right? That's where we're gonna start. Our BFS go to its neighboring but not visited one, and then once we get there, we'll check to see if they are smaller than, if they're smaller than this one, we'll push that one in, because that's where we're gonna go next, because we're always gonna go from the smallest, right? We'll always go from the smallest. So yeah, we do that. I have the remaining. Yeah, this is the remaining. The element out, height, ij. This is the 4 directions. If this is, and it's larger than it's not visited before, if it's smaller than this, we will have this, and then we'll push this one in. Maximum of h, and we don't have to do the maximum because we know this one's smaller. Well, it's smaller if it's not, right? If it's bigger, then we will just push. Yeah, we will push it in. So it's the maximum. So push it in, and then set as visited, remaining this, and then we go okay. Yep. So I do want to implement it. Okay, so we read the solution, but that doesn't mean we can be spared of the implementation. Okay, we still need to implement it. For 7, I knew immediately, okay, that I was not able to solve it. So I read my previous solution, right? My previous solution, as well as the solution of the 2D version of trapping rainwater. I understand it now, but I'm also sure that in a few months I will forget about it again. The key in both 2D and 3D solution is, right, to find the smallest of the edge. In 2D, that is simply the left and right boundary. In 3D, that is all the cells surround all the cells on the outer edge, right? The smallest edge determines how much water a new cell can hold above it. If the new cell has the smallest height if the new cell has a lower height than the smallest height on the edge, the difference between the heights is the amount of water capable of being held. Otherwise, we cannot hold any water on the cell. Once this is determined, we need to put the new cell in consideration. In a new cell as part of the edge, while popping the previous smallest cell. Yeah, because we are always moving inward, right? Always moving inward. So in 2D, there is no concept of popping, because we can simply keep track of the max on both sides. In 3D, however, we have to pop to give room for the newly encountered cell until surface, right, the currently lowest cell on the edge, we use a main heap. Okay, so we do need a std priority queue. We'll do a pair int and then a pair of int and int. We can actually make it easier by saying using chord pair int. So now we can just say this is the int and coordinate main heap height map size and height map 0 dot size. Std vector of chord dirs -1, 1, -1, -1, 1. It's not right. It's 1, 0. -1, 0. And then 0, 1. 0, -1. Okay, so fill the heap with all the heights around the edge. Okay, I0, I smaller than mi plus. We say min heap dot insert push. Yeah, push. So I0, 1, 2, 2. There's a height map. I0, I0. Main heap dot push. Height map. So the right is gonna be n-1. No, n-1. n-1. So j equal to 1, j smaller than n-1, j plus plus. Heap dot push. Height map 0, j. 0, j. So 0, j, m-1, j, m-1, j. Okay. Okay, so we fill it and then BFS to oh, also we need to say these are visited. So height map I0 equal to -1 visited. I n-1 equal to -1. J. This also equal to -1. Okay. So now in a BFS, right? BFS the whole height map, but the starting point is always the cell with the mean height in the heap, and we go all 4 directions, right? All 4 directions, and visit the next valid cell that has not been visited before, and based on its height against the lowest height on the edge, we decide whether water can be trapped above it. Yeah. Remain shall equal to m times n minus main heap dot size. So while main heap dot not empty and remain is larger than 0, auto const auto this height ij equal to main heap dot top. Yeah, I guess it's not possible. That's fine. So we just say auto element main heap dot pop. Height is element first, I is element dot second dot first, j is element dot second. Okay, ij. So for const auto di dj of dirs ni I plus di nj I plus dj. If I ni larger equal to 0 and ni smaller than m, nj larger equal to 0 and then nj smaller than n, and height map ni nj is larger equal to 0. That means we can visit it, right? If height map ni nj is smaller than h, then rest or plus equal to h minus height map ni nj. If it's larger, then we don't do it, but we'll always push it in min heap dot push. Ooh, I just realized main heap. So let's be negative. Actually, std max height map n9 and j, and then h. But this one need to be a negative value, and then ni and j. Alright, we'll push it in, and a height map ni and j is -1. So yep, so we and we'll say remain negative. And then once we're done, we'll return res. Okay, this is how we will do it. Let's see, it works. I forgot to do this part. What the hell? I don't understand. Which part did I not do right? Oh, I think I know. This is not here. Wait, hold a second. No, this is, right? This is remaining. We push one in, which means we have visited it. So yeah, it's right. That means we have visited. So every time we visit one, remain reduces. I don't know. It looks good to me. Yep. I'm back trying to figure out why it didn't work. I mean, this is how I wrote it before. It looks... I think the only possibility is this thing. So I am not going to do this. I am just going to say... and then I'll do dir first and dir second. Okay. This is the only one that I think is possible to cause the issue. Oh, well, I think I forgot to use to do that one again. What in the hell? That's not it. This is the same. Okay. Well, I did swap these, but it's the same thing. I don't understand. I do not understand. Like, what the hell? What happened? I don't know. I don't even know how to debug this thing. Because I don't want to debug it. And I think it will take a long time. So what I want to do is just, do this. Yeah, I got 1, 2, 5. Oh. 2, 5. Now I see. No, it doesn't matter, right? I don't understand why this one is not working. Yeah, we only have 4 in the middle. So this is the first one, get out. I cannot do anything. So this one basically don't do anything, and then we don't get anything. So this one is gone. And then 1, 1, 2. 0, 1. How is this one gets in? How is this one get in? What? Who get this 1, 1, 2 in? This is correct. We have 4 left. But you are doing 1, 0, 1. Oh. Hold on. 0, 1, 2. 0, 1, 2, 3, 4, 5. You're dealing with this. And direction. Right? So you either, so you go, you do this or do this. What in the world? This is bonkers, man. Something is not right. And I'll figure out what went wrong. I have 1, 2. Oh, shoot. Damn. Well, there you have it. Oh, I actually like to say DIDJ. Too fast. That's what's causing the problem. Okay. This one shall work. Yep, exactly. This one works. Ah, it's J. Well, it happens. That type of thing happens. Yeah, I'll have like a really good. Ooh. Pair is much better than the other one. 26 seconds. Wow. See, although we copy and pasted, there is still, room for improvement, and we did have some improvement. All right, that'll be